What's going on, guys? Stefan from App Stuff here. In this video, we are going to be going over binary search trees, and I'm going to go ahead and jump into an explanation of what they are. So a binary search tree is a node-based binary tree data structure which has the following properties. I'm just going to sum all this up. So we start with a parent node, and then each node we insert that is less than goes on the left, and each node that is greater than goes on the right. And the trick is every node that we insert is also a binary search tree. And what I mean by that is that say we were to insert 8 as our parent node and then 3 and then wanted to insert 1, it would go 1 is less than 8, which is less than 3, which is why it goes there. And 6 is less than 8 but greater than 3, so it goes on the right side of 3. So on and so forth. It's the same thing for the right. So this is a really common data structure. It's common to get asked questions about this in interviews for any developer job really. And it's good to familiarize yourself with this data structure, how to traverse through it, search through it, understand how it works, and all that good stuff. And we're going to be getting into all of that in this video here. So let's go ahead and get started with a new playground. If you guys don't know how to do that, just go up to File, hit New, and then go to Playground. And let's get started with our class declaration. So we're going to say class binary search tree. And we need a couple properties. So each tree is going to have a value, which is going to be an integer. And then we need a left and a right node. So we're going to say left. And if you guys remember from the explanation, each node that is on the left or right has to also be a binary search tree. So do it like this. And we're making it optional because not every tree has to have left or right nodes. You can have a tree that is a leaf, which means it has no nodes. You could have one left but not a right, so on and so forth, which is why we make those optional. We also need to keep a variable for our parent node, which is also a binary search tree. And to initialize, we are just going to do that with a value, which is going to be an integer. And we're going to say self.value equals value. So now we can go down at the bottom here and say let tree equal binary search tree, and then pass in a value, and let's do 8, just like we saw in the example on the internet. Okay, so now we need to create a function to be able to insert nodes into our binary search tree. So let's go ahead and do that. Create an extension for our binary search tree, and we're going to write a function called insert. And it's going to take in a value, which is going to be an integer, and a parent, which is going to be a binary search tree. Open, close parentheses. So if you guys remember from the conditions of a binary search tree, if the value we're inserting is less than, it needs to go on the left, greater than, it needs to go on the right. So this is how we're going to do that. We're going to say if value is less than self.value, oops, open, close bracket. And then if value is greater than, so let's actually, instead of doing that, we can just write an else statement. Okay, so let's get some space going here, and this is what we need to do here. So we need to check and see if a left node exists already. Okay, so we're going to say if let left equals left, and then we're going to say else. And we need to do the same thing for the right side. So we're going to say if let right equals right, else. And again, guys, we do this because we need to check and see if a left node already exists. And if it does, then we need to go and append our value accordingly to that left node. If it doesn't, then we're going to create our initial left node. So we're going to say let left, or sorry, not let left, just left equals binary search tree value, and the value that we're passing in. So if a left node doesn't exist, which right now it doesn't, then it's going to hit this else block, right? If the value is less than, if the value we're inserting is less than our parent value, and then it's going to say, okay, our left node, which is this guy up here that we declared in our class, is equal to a binary search tree with the value that we are passing in through our function. And we're going to do the same thing on the right. So just copy and paste that line of code, and now just say right. And now this is sort of the tricky part. We're going to use some recursion here if a left node already exists. So I'm going to go ahead and type it out and explain it in a little bit. We're going to say left.insert value, and the parent is going to be self. And then right.insert value, parent is self. Okay, so essentially what's happening here, guys, is if the left node already exists, it's going to hit this case here if our value is less than our parent value, right? And then it's going to call this function again. So essentially this function is going to start all over. And then it's going to say, okay, this new value that we're inserting, is it less than the value that we're looking at? And then if yes, it's going to just go through this logic all over again to insert that new node accordingly to the left or right node that already exists, okay? So that's how we use some recursion there. I know it might be a little confusing and it might not make sense yet, but if you guys think about it and as we go on, it's going to make more sense. Okay, so now let's go ahead and insert some new nodes into our tree. So we're going to say tree.insert. Oop, I forgot some lines of code really quick. Here we need to declare the parent node, right? So we're going to say left.parent equals self and right.parent equals self. Okay, so when we first insert that left node, we need to make sure we set the parent node. So let's say we inserted 6, the parent node would be 8. And when we're saying self, we're just referring to the node that we, or the binary search tree that we originally created. Okay, so you guys will notice that we're gonna have to pass in a parent value each time we call this function, which is kind of annoying, right? So we can actually go ahead and do a pretty cool trick here. If we just want to insert by value, we'll say, go ahead and create another function called insert, pass in a value, which is an integer, and then call this function down here. And the parent is always going to be equal to that self or that node that we originally created. So we can just say insert value, and the parent is going to be self. So this way we can just call this function now without having to pass that parent value in every single time. You guys will notice though that when we say tree.insert, both methods show up. So if we want that only this one to show up, we can go ahead and make this a private function. And since this is part of an extension, it is private to this extension here. So now when we say tree.insert, that only this method is going to come up. So now let's insert 6 and then tree.insert 10. Okay, so now we have a little binary search tree going here. Now we need to be able to print our tree out so we can see what's going on and sort of debug everything, or just it'll help us understand what's going on to see a visual representation of our tree. So if we were to say print tree and hit play, we're going to get this weird message here. So what we need to do is write another extension and conform to our custom string convertible protocol in order to print our tree out. And that's what this is going to look like here. So go ahead and create another extension for our binary search tree. And this is going to, like I said, conform to our custom string convertible protocol. And this just requires us to implement a description variable. And now we're going to use this to print out our tree. So it's a little tricky, but this is what it's going to look like. So we're going to say var result equals an empty string, and then go down here and just say return result. And we are going to append values to the string as we go. Okay, so we want to start with the left side and then print our root value in the middle and then print what's on the right side. So we're going to say if let left equals left. We're going to say result plus equals, and we're going to interpolate the string left.description. And again, we're using recursion here, and I will explain what's going on with that in just a second. So then we're going to say result. So that's the left side of our tree. Now we're going to say result plus equals value. That's going to give us our parent value. And now we are going to say, we can just go ahead and copy and paste this and change all the lefts to say right. Okay, now let's go ahead and print out our tree and see what we get. So it's not exactly how we want it yet, but there's our root value, there's our left node, and there is our right node, right? So essentially we just want some arrows pointing to our values here. So here we're going to just do this. I think it goes over here. And then here we're going to do this with a space. Now print our tree. We want the space there as well. Okay, so you guys will notice now this is our root node, and then it has pointers to our left and right nodes. And that's about as good as our description is going to get. It's not the best, but it'll do essentially. So let me go ahead and explain the recursion before we move on to searching. So it's going to say as long as a left node exists, then we're going to append this left.description. So it's going to start this description variable over and then just go through this process again until there are no more left nodes. And then it's going to, just like I said, keep going through until it finishes printing out our tree. And we use recursion for the left and right values because we're not sure when it's going to run out of left nodes or right nodes. Okay, so now that we have that done, let's go ahead and write a function to search through our tree. So we're going to say extension binary search tree, and we're going to say func search for value int, and we're going to return a Boolean variable to determine whether or not our search was successful. So go ahead and type return false down at the bottom. That's going to be our default value. And then if we find our value, we'll tell our function to stop and return true. Okay, so let's go ahead and say if value equals self.value, return true. So this is going to be for when our when we find the value that we're looking for, we're just going to stop and return true. Okay, so essentially what we need to do now is iterate through the entire tree, go through all the left nodes, all the right nodes of each individual tree and see if we find our value, right? And because we know that values less than our parent node are going to be on the left and vice versa for right, that allows us to simplify our search a little bit. So we're going to say if value is less than self.value, and then we can say else. So give us ourselves some space here. And we're going to be using recursion again. So guys, we use a lot of recursion with this binary search tree, so it's a really good concept to familiarize yourself with. I know it takes a little bit of time to wrap your head around if you're not familiar with it, but the more you think about it and the more you do it, the more sense that it makes. So we're going to be using recursion for this as well. So we're going to say if let left equals left, then we're going to say return search left.search for value. And then down here we're going to say if let right equals right, return right.search for value. Okay, so let's go ahead and see if this works, and then I will explain what's going on with our recursion in a second. Let me just clean up all that white space. Okay, so let's go ahead and say tree.search for value 6. And it gives us back true. Let's search for our parent node. Gives us back true. Search for 10. Gives us back true. Okay, now let's search for a value that's not in there. Gives us back false. So that search is working really nicely there, guys. So I'm going to go ahead and go over a quick explanation of what exactly we're doing here. So first, we want to check and see if the value we're searching for is equal to our parent value right off the bat. That's what that self.value is. And if it is, we're going to return true. If it's not, we're going to check and see if that value is less than our parent value. So if we're searching for 6, it's going to hit this block here. Okay, and then it's going to check and see if a left node even exists, right? Because if it doesn't, then we just stop our search, right? So in this case, a left node does exist, and it's 6. So we're going to say return left.search, right? So we type this left.search because our left node is 6, and it's going to recursively call this function again. So it's going to start this function over, and our self.value is now equal to 6 because we're calling search through our left node, not our parent node anymore, right? So it's going to say, okay, the value that we're searching for is now 6. It's equal to our self.value, which is equal 6, and we're going to return true. And the same thing goes for the right. So let's go ahead and insert a couple more values. Insert 4, tree.insert 12, print our tree. So now we have 8, 6, and 4, 8, 10, and 12. So one more time, I know I'm abusing this explanation a little bit, but this is for those of you who don't really understand what's going on. If we were to run through this function and we're now searching for 4, right? It's going to say, okay, it's not equal, these are not equal, but it's less than our parent value. So now it's going to go to 6. And then, because it hits this block here, where it says if let left equals left. So a left node exists. Then it's going to say, okay, return left.search. So now it's going to run that search function for 6. And then, okay, this does not get hit because we're searching for 4, right? So this now becomes, is 4 equal to 6? And so that's not true. So it's less than that. So now it's going to say, okay, we have a left node, and then we're going to do the same thing for 4, and then it's going to recursively call that again, and then this value is going to now, this condition is now going to be met. We're going to return true. So that's how the search function works, guys. The same stuff holds true for the right side, and if it goes through that entire tree and doesn't find the value, it's going to return false. So that's our search function, right? Now what we're going to do next is write some functions out to determine the depth of our tree, or sorry, the height of our tree, the depth of a particular node. So the height of a tree being like how far down does this thing go. If we want the depth of, say, 10, we want to see where 10 is in the tree. And then we're going to determine the minimum and maximum values of our tree as well. So let's go ahead and write an extension to do that now. So we're going to say extension binary search tree again. And first we're going to start out with functions to determine the minimum and maximum values of our tree. So let me go ahead and write the func for maximum 2. Damn it. Okay, now these are both going to return integer variable or values. Dude, I cannot type right now. Sorry, guys. Okay, so we essentially, the minimum value is going to be the leftmost node of our tree, and the maximum value is going to be the rightmost node of our tree. So we want to just keep going down through the tree until we no longer have any more left nodes, and then return that leftmost node. So we're going to use a while loop to do that, guys. So we're going to say var node equals self, and then we're going to say while node.left is not equal to nil. Actually, no, let's use a while let loop. So this is a really cool thing that you don't see a lot. So we're going to say while let left equals node.left. We're going to say node equals left. And then we're going to return the node.value. Okay, so brief explanation of what's going on here really quick. We're creating a variable that stores the value for our parent, like, binary search tree, right? So it's a variable that stores all of this information. And we're going to say while let left is equal to node.left. So we're creating this constant here that is essentially saying while our left node is not equal to nil, store that whatever that left node is in this value. And then inside of our loop, we're going to set this node here to equal that left node. Okay, so let's run through this really quick. This is the node that we start with, and then it's going to go, it's going to say, okay, we have a left node, so this condition is met, and it stores that left node in this value here. So it's going to go to 6. And then it's going to say node that we started with, which was equal to this entire thing at first, is now equal to the binary search tree of 6, which now narrows it down to just 6 and 4. Okay, and then it's going to start over, and it's going to repeat that same process until we get to 4, and then this while loop is not going to be infinite because 4 is not going to have any left nodes, so this condition will not be met, and then it's going to return that node.value, which will be 4. So we can go ahead and copy and paste all this, put it in our maximum function, and just change this to right, right, and right. And that's going to give us our maximum value. Okay, so let's go ahead and test this out. Our max should be 12, our min should be 4, right? So let's go ahead and say tree.minimum and tree.maximum. And tree.minimum, we get 4 right here on this console here, if you guys can't see that, and tree.maximum, we get 12. So that works really nicely, guys. Now we are going to write a function for our height and our depth. So let's go back up to this guy here, and we're going to say function height, and that's also going to return an integer value. And then we're going to write a function to find the depth of a particular node of value, which is going to be int. Okay, so say we wanted to find the depth of 10, then we could pass 10 into this function, and it would give us, and it would say, okay, it's one iteration down. And that's also going to return an int. Okay, so let's get started with our height function. Okay, guys, so first thing we need to consider is like our base case of when we just have a tree that is only a parent node. And which is essentially the same thing as a tree that does not have any left or right nodes. And that's going to be called a leaf. So we need to create this variable called isLeaf to determine whether or not a tree has a left or right node. Or if it has any left or right nodes, rather, because if it doesn't, then we're going to want to return 0. So let's create this value up here. We're going to say var isLeaf of type bool, open close bracket. We're going to say return left equals nil and right equals nil. So this is going to give us back true if there are no left and no right nodes, right? So and if that is the case, we're going to say return 0, because our tree will not have any, it won't have any height. It's just a singular parent node. Go down here and say return 0 as well. And here we're going to say else, and just say return 0 for now so we can run our code and see that this works. Or here, say return 1 so we can see if it's hitting this block. Go ahead and comment out these lines. Let's say print tree, and it just gives us back 8. Now let's say print tree.height. It's going to give us back 0. And if now because it's hitting that isLeaf block because we had no left and right nodes, now if we do this, it's going to hit 1, which is hitting our else block. Okay, so that's what we want. Now we're going to be using some more recursion to determine the actual height of this tree. The height being how many nodes it has, right? Or how far down the tree goes. So we're going to say return 1 plus, and then we're going to want to determine the maximum between the left height and the right height. So essentially it's going to say give us back 1 plus, and like, because we don't know if there's going to be more left nodes than right nodes, so we need to determine the maximum value between the left height and the right height, right? So when we call this recursively, let's go ahead and print our tree out so that we can see how this works. And we're going to need to give it an optional, a default value. So just go ahead and give it a default value of 0, and do the same thing for our right side, because these left and right nodes are optional. We don't want to force unwrap them because it might cause a crash. So now let's go ahead and print our tree so we can understand what is going on here. All right. And let's add another value to the left. So let's add 2. Now print our tree. Actually, no, let's add 5. Okay, now just run this. Okay, so now this is what's going on. We go 8 down to 6, and then we actually go down to 4, and then since 5 is greater than 4, 4 now has a right node of 5. I know it's not the best like visual representation, but I think you guys get what's going on more or less. So now let's go back up here and start going over what exactly is going on in this function here, because this is like kind of confusing to understand. So it's going to start at 8, right? And then it's going to say, is that tree a leaf? And it's going to say, no, it's not. So now we're going to hit this else block, and it's going to return 1 plus the maximum value between the left height, which is the height of 6, and the right height, right? Which is this 10 here, okay? So it's going to then re-execute this function, and it's going to go down to 6, and it's going to say, okay, is 6 a leaf? No. So it's going to hit this else block again. So then it's going to increment that value by 1, or so the value we're returning by 1, because it's hitting this 1 plus again. And then it's hitting this this section of code again, which is getting the max value between the left and right heights, right? So because the right doesn't exist for 6, it's going to hit this default value, which is 0. So that's why we put that there. And then it's going to just keep going down the line. It's going to say, then go down to 4, and then it's going to say, is 4 a leaf? No, it's not, because it has 5 as a right node. And then it's going to hit this block again. That return value is going to get incremented again by 1, and then return the left this maximum value between the two things. And originally, our left and right max or heights were, we have this guy in there as well, and that's incorporated to this max between our left and right heights, right? So then it's going to say 5 is finally a leaf. We return 0. And then, so that recursion is over, and it's going to return us the value or the total of our height from all those 1 plus whatever, plus whatever, plus whatever, right? And give us back our height finally. So that's sort of how that works. I know it's kind of confusing, but I think if you explain it enough in your head, it will make sense. Okay. Now we're going to go and calculate the depth of a particular value. So say we wanted to calculate the depth of 10. It only goes down 1 iteration of the tree, so we would want to return 1. So let's go ahead and start coding out what we need to do to calculate that. So let's go ahead and create a variable here guys, called depth, and we're going to set that equal to 0, and go down here and just say return depth. Okay, so we need to do something tricky for this function, and I'll explain why in just a little bit. First off, we need to determine if the value that we're looking for to determine the depth of is even in the tree. So we're going to go back up to our search function, and we're going to create a new one. So just go ahead and copy all this stuff, paste it there, and instead of returning a Boolean variable, we're going to return a binary search tree, and this is going to be optional. And then call this search and return tree. And everywhere we have Boolean variables being returned, just say return self. And down here, if the search is unsuccessful, we're going to return nil. And then we need to replace search with search and return tree. Okay, so you guys are probably like, what in the hell is going on? And it's actually pretty simple. And we're going to see what's going on here by typing out print self in this initial if statement here. So essentially, this is going to search for a particular value, and it's going to return a binary search tree that value is a part of. Okay, so let's go down here and let's say tree.search and return tree for value, and let's do let's see, which one do we want to do? Let's do 4. Run. Okay, so 4 exists within our tree, and the only child that 4 has is 5, right? So what that search and return tree is going to do for us is actually give us back the tree, or only give us back the children of the tree that we're looking for, or that of that value, right? So we were looking for 4. 4 has 1 child, which is 5, and it's going to give us back that value. Now, if we were to look for 6, you'll notice it gives us back the tree associated with 6 that has 6 as the parent, right? So it's 6 and then down to 4 and then down to 5. So we'll see why that's going to be useful here. So because that function up here returns an optional value, we need to unwrap it. So we're going to say guard let tree equal search and return tree for value, and actually go up here and type in value, and this is going to be the value that we pass into the function, or essentially the value that we are looking for to calculate the depth of. And if it's not there, we're going to just return 0, right? Okay, so now we need to run a while loop to and I'll explain why once it's done. So we're going to say while let parent equals tree.parent, and then we are going to say tree equals parent, and we're going to increment our depth by 1. Okay, so what is going on here? Well, first we're going to get an error, and we actually need to make this a guard var statement because we're mutating this tree, right? So let's go ahead and run our function, and then I will explain what's going on. So let's run this guy. We notice that 6 is 1 level down, and that's correct. So let's check 4. It should give us back 2. That's correct. Check 3, which is some value that's not in the tree, gives us back 0. So that's looking good, guys. Now let me explain what's going on here. Oops, passed it. Okay, so we're essentially finding the tree using the search and return tree function, and once it finds the tree, it gives us back that tree and all the associated children. To find the depth of that tree, we actually just keep going up the hierarchy until a parent no longer exists. That's what this while loop is doing. And we have to mutate that tree because we have to stop once we get to the root node. So it's going to say, okay, we found your value. Does it have a parent? Yes. Okay. Make that parent the new tree that we're looking at. Okay. And then it's going to increment our depth by 1. And then it's going to stop once it hits the root node. Okay. So say we were looking for 6. 6 has a parent, which is 8. So then it says, okay, depth is now 1. And then once that while loop goes to run again, it says, oh wait, 8 does not have a parent. It's the root node. Stop. So that's how that works there, guys. And I'm actually going to stop this video here because it's getting kind of long and it's a lot to wrap your head around. I'm going to do a part 2, and the features we're going to be implementing there are tree traversal, and we are going to be removing nodes from our tree as well. That's the last 2 things we're going to do. Then I'm going to do a generic wrap up of everything we've done, and that is going to be my Everything You Need to Know series on binary search trees, guys. Hope this was helpful for everyone. Don't forget to hit the subscribe button down below. There's going to be a ton more videos on not just algorithms, but tons of like cool beginner apps, intermediate apps, advanced apps, all that stuff. So stay tuned for more videos, guys. Thanks for watching. See you in part 2.